The Utah Robot Kit, or ERK, was designed and built as part of an ongoing project in computer-aided prototyping at the University of Utah. The aim of that project is to create an interdisciplinary prototyping environment that coordinates radically different types of information such as VLSI, CAD, CAM, robotics, and control. ERK was used as a case study to explore the basis for building such an environment and was a cooperative effort between several university research groups. A low-cost, fully functional robot, ERK will be used as an educational tool for robotics and control classes. Method for control, simulation, and error analysis were first tested with a simple one-link robot in the form of a motor with a load. The motor was controlled with a PID controller whose I/O card was connected to a PC. Benchmark tests for the controller were run on 4 platforms to determine several things: what bottlenecks might be in the system, what parts of the system should be done in hardware, and which of the platforms was most suitable. 3 additional experiments were run with a one-link robot. In each, a trajectory was specified by the user and position and velocity measured with sensors in the robot's joint. A graphical interface was developed to display desired and measured values for position and velocity and the computed error between them. Here, a motor is shown on the right side of the screen as it is being controlled. The interface is shown on the left side. The Alpha 1 system, developed at the University of Utah, was used to design the mechanical structure of the robot. In addition to its many other capabilities, the Alpha 1 system supports mechanical features and the automatic generation of NC code for milling machines. This code was used to mill the robot's structural components in the university's Advanced Manufacturing Lab. ERK was designed to be a low-cost, relatively quick 3-link robot. The first joint is revolute about an axis perpendicular to the mounting structure's plane. The second and third joints are also revolute about an axis parallel to that plane. The third link was designed to be replaceable, allowing alternative configurations. Each joint is driven by a separate motor and contains sensors for position and velocity. The entire system, including motors, was modeled for purposes of layout and assembly analysis. The structural members are milled from aluminum with pockets for weight reduction. ERC is controlled with an analog and digital PID controller. This can be connected to either a PC or Unix workstation. A graphical user interface was developed that allows monitoring of and interaction with ERC's PID control system. It can be used with an actual robot or with a simulator. This session shows the system in simulation mode. The system has a user-friendly interface that enables the user to change any of the control parameters interactively. Parameters that can be changed in this package include forward gain, proportional gain, differential gain, integral gain, input trajectory, and update rate. Individual joint positions can be changed with slider bars. It also serves as a monitoring system that provides several graphs and reports. In addition to displaying graphs and text, the system displays an animated picture of the robot's desired position and of its position resulting from the current control parameters. This provides the user with continuous intuitive feedback. The system was designed in such a way that it can be used with any PID control system. Its simulation capabilities and intuitive graphical interface, together with its report generation facilities, make it a flexible teaching or research tool. This session shows a real-time demonstration of ERC control. The bottom left window shows the actual robot. The upper left window shows a model of the ERC with a continuously updated positions as measured by joint sensors. The upper right shows the position requested by the user. In this example, the user is interactively specifying the trajectory for each joint using the slider bars in the center of the screen. Alternatively, predefined trajectories may be used. The history of any parameter can be displayed as a graph at any time. With this system, the user can easily modify control parameters, specify movement, and observe the effects of various control settings on either a real or simulated robot. This session shows an experiment where a predefined trajectory is supplied to ERC. The Utah Robot Kit was developed as a case study in electromechanical system prototyping. Its design process was examined in detail and used in the development of an interdisciplinary prototyping environment. This, the Utah Prototyping Environment, or OOP, enables the concurrent design and modification of electromechanical systems and facilitates communications between the various groups involved in such a process, including design, robotics, structural engineering, control, electronics, simulation, supply, manufacturing, and assembly. We believe that the ERC is economical, fast, and with the interfaces we have developed, an easy-to-use system. As such, it is well suited for use in the classroom or in a research environment. We are currently in the process of making the Utah Robot Kit available to interested institutions.